Stirling cycle. The cycle has 4 processes, out of which 2 are reversible isothermal processes and other 2 are isochoric, that is reversible isochoric processes. The cycle could be indicated on PV diagram as (1 to 2) is isothermal compression, 2 to 3 is constant volume heat supply, 3 to 4 is isothermal expansion, in which again there is heat supply, 4 to 1 is constant volume heat rejection, and 1 to 2 is again isothermal compression, heat must be rejected. The cycle could be represented on TS plane also, TS plane also, like 1 to 2 is isothermal compression, therefore heat must be rejected, entropy should decrease but the temperature remains constant. 2 to 3 is constant volume heat supply, where the temperature and as well as entropy both increases. 3 to 4 is isothermal expansion, where heat is supplied, temperature is constant and entropy increases in 3 to 4, and 4 to 1 is again constant volume heat rejection. There are 2 constant volumes, there are 2 constant temperatures. For ideal regenerative Stirling cycle, that is heat rejected in the process, that is constant volume process, could be transferred to heat supply in the process 2 to 3, that is with infinitesimally small temperature difference during heat transfer, that is reversible heat transfer. Then thermal efficiency of regenerative Stirling cycle shall be equal to the thermal efficiency of Carnot cycle. So the important point to be remembered is, if there is regeneration, as I have shown in the arrow in the TS diagram, Q transfer, heat transfer, in the heat rejected in the 4 to 1 process in the constant volume, if it could be transferred to the process 2 to 3 in the constant volume process, with no entropy generated in the universe. Such heat transfer can be called as a reversible heat transfer. Then the only heat transfer sectionally shall be during the process 3 to 4 and during the process 2 to 3 under isothermal conditions. Then the thermal efficiency of the ideal regenerative Stirling cycle will be equal to that of the Carnot cycle, which is equal to 1 minus TL by TH, where TL here is temperature of the sink, that is T1 is equal to T2, TL that is TH will be T, which is equal to 3 is equal to T4. In fact, hot air engines can be taken as an example for Stirling cycle. Now I shall discuss about the Rigum cycle. This cycle has 4 processes. 2 of them are reversible isothermal processes, that is isothermal compression and isothermal expansion, and the other 2 processes are isobarics, reversible isobarics. The cycle could be represented on PV plane like this. Isothermal compression, constant pressure heat supply, and isothermal expansion and constant pressure heat rejection. 1 to 2 is isothermal compression, where heat must be rejected. 2 to 3 is constant pressure heat supply. 3 to 4 is isothermal expansion with heat supplied to the system. And 4 to 1 is isobaric heat rejection, reaching back to the initial state. So 1 to 2 is isothermal, 3 to 4 is isothermal, that is PV is equal to constants. 2 to 3 is isobaric and 4 to 1 is also isobaric. The cycle could be represented on TS plane like 1 to 2 is isothermal heat rejection, 2 to 3 is constant pressure heat supply, 3 to 4 is isothermal expansion, 4 to 1 is isobaric heat rejection. Here also regeneration, if provided, between the processes 4 to 1 and 2 to 3 with infinitesimally small temperature difference, that is delta T tends to 0. Such heat transfer is also called as reversible heat transfer with no generation of entropy in the universe. Then the thermal efficiency of ideal regenerative, more correctly, Ericsson cycle is equal to that of thermal efficiency of Carnot cycle operating between same temperature limits. So I can write that in the bottom line is thermal efficiency of the regenerative Stirling cycle is equal to thermal efficiency of regenerative Ericsson cycle is equal to thermal efficiency of Carnot cycle. All the three cycles can be thought of as reversible cycles. All the reversible cycles will have same thermal efficiency when operating between same temperature limits. Another example for the Ericsson cycle can be taken as ideal Joule cycle with infinite stages of multi-stage compression with intercooling and with the infinite stages of multi-stage expansion with reheating. An ideal Joule cycle could be thought of as Ericsson cycle. If you provide infinite stages of compression in the ideal Joule cycle, and also if you provide infinite stages of expansion with reheating in the same Joule cycle, the cycle would finally gets reduced to that of Ericsson cycle. This is an important note to be noted here. Now let us do a problem on Brayton cycle. In a simple gas turbine plant operating on air standard Brayton cycle, the air enters the compressor at 0.1 megapascal 300 K and leaves at 0.6 megapascal. The maximum temperature of the cycle is 1200 K. Determine the cycle efficiency and work ratio. Let us indicate the solution is given like this. Let us indicate the cycle on temperature entropy plane. The cycle has two isoentropics and two isobarics. This is a work of turbine in the process 3 to 4. In the process 1 to 2, this is work of compression, heat supply. This peak temperature is given as 1200 Kelvin. The pressure ratio of cycle is Rp is equal to P2 by P1 is equal to 0.6 divided by 0.1, that is 6. For compressor, let us calculate the work input first of all. The 1 to 2 is isoentropic compression. Therefore, the temperature ratio can be written as P2 by P1 whole to the power of gamma minus 1 by gamma, implies T2 is equal to 300 into 6 to the power of 0.4 divided by 1.4. The T2 is 500.5 Kelvin. Work of compression is equal to H2 minus H1. That is Cp of air is into T2 minus T1, that is 1.005 into 500.5 minus 300. This is equal to 201.5 kilojoule per kg. This is the work of compression. So similarly, let us obtain the temperature after the expansion in the turbine. 3 to 4 is isoentropic expansion. Therefore, writing the temperature ratio is equal to P3 by P4 whole power gamma minus 1 by gamma, that is Rp to the power of gamma minus 1 by gamma. Therefore, T4 is equal to T3 divided by Rp to the power of gamma minus 1 by gamma. T3 is given as 1200 maximum temperature divided by 6 to the power of 0.4 divided by 1.4. T4 is obtained now as 719.2 Kelvin. Therefore, work of expansion by the gases in the turbine is equal to H3 minus H4, which can be written as Cp of air into T3 minus T4. That would obtain as 483.2 kilojoule per kg. Heat supplied in the constant pressure process, that is heat supplied in the process 2 to 3 is H3 minus H2, which could be calculated as Cp of the air into T3 minus T2. T3 is given, T2 is calculated. The result will be around 699 kilojoule per kg. Therefore, thermal efficiency of cycle is net work done per cycle divided by heat supplied, that is work of turbine minus work of compressor divided by heat supplied. This will be equal to the 40.3% approximately. Work ratio is equal to work of turbine minus work of compressor, that is net work output divided by turbine work. This results in 0.583. That is 58.3% of work output is obtained out of the total turbine work. Remaining 41.7% of turbine work is consumed by the compressor even in this ideal Joule cycle. That is the drawback of the gas turbines power plant, because around 40%, 35 to 40% of the turbine work is used for driving the compressor. Remaining 58 to 60% of turbine work only will be obtained as the net work output of the cycle. Now let us solve some of the objective questions which were given in the IES papers. Objective question: the air with enthalpy of 100 kilojoule per kg is compressed by an air compressor to a pressure and temperature at which its enthalpy becomes 200 kilojoule per kg. The loss of heat is 40 kilojoule per kg from the compressor. As the air passes through it, neglecting Ke kinetic energy and Pe that is potential energy changes, the power required for a air mass flow of 0.5 kg per second is A 30 kilowatts, 50 kilowatts, 70 kilowatts, D 90 kilowatts. The solution to this problem could be given as it is the compressor. The air is entering with an enthalpy H1 of 100 kilojoule per kg. Air is leaving with exit enthalpy H2 of 200 kilojoule per kg. There is heat rejection 40 kilojoule per kg, which is taken as negative because heat is rejected from the system. The symbol should be negative. Let us calculate what is work input by writing steady flow energy equation to this steady flow open system, that is Q minus W is delta H plus delta Ke plus delta Pe. Changes in Pe and changes in Ke are neglected. Q is equal to minus 40 minus of W, that is work done per kg, is equal to H2 minus H1, that is 200 minus 100. Therefore, minus W is equal to 100 plus 40, that is 140 kilojoule per kg. Minus sign of W indicates it is work done on the system. Of course, compressor needs to be done on it. The power input to the compressor is equal to mass flow rate of air into work done per kg. What is the mass flow rate of air given? 0.5 kg per second into 140 kilojoule per kg. Kg gets cancelled. You will get 70 kilowatts of power is required for driving the compressor. Now next problem is another objective question. In which one of the following working substances does the relation T2 by T1 is equal to hold good if the process takes place with zero heat transfer. A, wet steam. B, superheated steam. C, petrol vapor and air mixture. D, air. Because the solution could be given like this, because Q is equal to 0 implies the process is adiabatic, and assuming a reversibility in the process becomes isoentropic. Therefore, writing a isoentropic relation T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma. For air, gamma is 1.4. So, the answer is with air. For superheated steam, the adiabatic index gamma is only 1.3. It is not 1.4. So, the answer would be air. Now, I shall discuss about another gas power cycle known as Atkinson cycle. It is only a slight improvement or change in the Otto cycle. The cycle is represented on the PV diagram like this. One to two is isoentropic compression. 2 to 3 is constant volume heat supply, just like in Otto cycle. And 3 to 4 is isoentropic expansion down to the same pressure as the beginning, that is P4 is equal to P1. In the case of the Otto cycle, the expansion would be stopped somewhere here, but in the case of the Atkinson cycle, the expansion would continue down to the initial pressure, and then last process is isobaric heat rejection completing the cycle. 1 to 2 is isoentropic compression. 2 to 3 is isochoric heat supply. 3 to 4 is isoentropic expansion. 4 to 1 is isobaric heat rejection. Just like any other cycle, here also thermal efficiency can be calculated as 1 minus QR divided by QS. Heat rejection will occur at constant pressure, therefore Cp into T4 minus T1 divided by heat supply will occur at constant volume, therefore Cv into T3 minus T2. Remaining parameters being same, that is peak temperature, compression ratio being same, that is for same peak pressure and peak temperature and for same compression ratio or thermal efficiency of Atkinson cycle would be greater than that of thermal efficiency of Otto cycle, because the expansion being complete, the expansion is being up to the inlet pressure. The area of the PV diagram, the enclosed area of the cycle, that is net work done per cycle, will be more in the Atkinson cycle than in the Otto cycle. The enclosed area of the cycle on PV plane means net work done per cycle. Because the enclosed area is more in the Atkinson cycle, work done per kg shall be more. Therefore, for the same heat supplied, thermal efficiency of the thermal efficiency of Atkinson cycle shall be more than that of thermal efficiency of Otto cycle.